Okay, so I'm sure you maybe have heard of IBM. I hope so. But our business model is essentially to solve problems for enterprises with technology, and we break that down. We essentially do that through hybrid cloud, data, and AI software. And our goal is to build software predominantly, including partnering with a company we own called Red Hat, you may have heard of, to essentially build middleware and tooling software, things like databases, messaging, etc., that can essentially be deployed anywhere, any cloud, any hardware infrastructure on premise. And a lot of our software is either cloud native, engineered ground up, or been reinvented, and of course now is AI powered. Now, Erol and I work in some of the largest of the companies in Australia, particularly the banks. And today, some of the topics really, I guess who here knows about RAG and GraphRag? Has already played with it? So a few people, okay. It's one of those things, if you look at LinkedIn, it's been on there for like years, and everyone's doing it, everyone's, so much noise on LinkedIn. It's funny when you actually get inside these banks, they're doing lots of experiments, they're playing with all the cool tech, but they're not necessarily rolling things out into production. So even though some of the things we show today might be a little bit basic, they are sort of really some of the grounding and starting points that we look at. So I think in the context of what I get in today, I'll speak for a few minutes, then Erol's going to do a demo. There's all sorts of things to think about when you're rolling out an AI-powered system or some sort of system that involves AI. But I think in the context of today's talk, three things. Think about the model you're using. You don't always use one model, and it isn't the biggest model on the block from our friends that are out there. The industry is shifting to specific tasks built using particular sizes of generative models. So machine learning models clearly have been around for a long time, and they do exactly what we need them to do. But in the generative space, people are still finding their way in terms of what model to use for what task. Then when it comes to actually utilizing that model for whatever you need it to do from a generative perspective, is RAG or fine-tuning. So I'll explain what RAG is in a minute, retrieval-augmented generation, or fine-tuning. And people say, is it either or? And our stance is, well, actually, it's both. If you're building a material system that's going to be running for, serious critical workload, then fine-tuning a foundation model, an LLM, with your information is essentially giving that model your voice. So think about ingesting all the information and structure and knowledge about your company or your industry. That's fine-tuning. Whereas RAG is essentially in-context data that can be given to the model when you interact with it to give it up-to-the-minute information to help you have that better interaction. Clearly, a lot of the interactions we're doing today are through chatbots and what have you, but if I didn't say the word agentic today, then I'd be shot, because everything's agentic these days. Agents are essentially digital humans doing various tasks for us. Anyway, let's get into it. So retrieval-augmented generation. So the concept is that I want to talk to a large language model. We know the vision models and other things like that, and audio and what have you, but let's just think about the large language models like Anthropic Claude and the big llama models, that type of thing. And we're going to ask a question, and we're going to get the response back. And you do this. We do this all the time. We go to these models, we chat with them. But what RAG does is brings in some information that's relevant to the query. So, for example, if we're using a large language model like Claude, but we might have built an in-house enterprise system, AI system for HR. So the in-context information that's inside this system is essentially all the HR records about employees, policies, that sort of thing. And what happens is during the question and answering process or the interaction with the model, the system goes away and finds the relevant information that's in context to that question. So if, let's say they're asking a question about Jeremy's employment history, and it will go and find relative information and then use the power of the large model to build a much more meaningful response to the question, as opposed to, who? Jeremy Caine? Never heard of him, which is what Claude might say. So I'll just break this down briefly, and then we're going to show you some code in action. So think about, okay, so how do I get the information? So think about these employee records in this example for HR. How do we get those into a store so that we can use it at a retrieval process? So you hopefully heard some of these phrases that have been popping up in the last year or two, few years. But we take some input content. Now this can be anything. This can be extracts of data from databases. It can be web pages, PDF documents, you name it. And we go through we can use various tools and technologies to split that information. So we read in these files, we read in these data sets, and we split them into regular sized chunks, which is basically just breaking down the information into smaller pieces. And if you've done any of this programming, you'll know that when it gets to things like PDFs, it actually gets quite hard to split them out meaningfully. But we'll talk about that in a minute. And then once you've got the chunks of information, we then need to add interesting information about that text to it. So we add metadata to it. So in that process, we end up with a document set. Not to be confused, of course, with the document that you ingested at the beginning, but that's the phraseology that we use, chunks and documents. And then we use a small model, an encoder model, to basically create what's called vector embeddings. So we convert that text into numbers, essentially. And those numbers are vectors. If you remember your maths from school, vectors have got lots of lines and angles between them. But the numbers are essentially stored, and the numbers represent the meaning of the text. So we're going to use an example around the State of the Union speech by Biden a few years ago. So it's going to have information about, or pieces of speech about conflict, Ukraine war, COVID, American economy, that type of thing. So now the words that have been turned into numbers, that have gone into this vector store, have been turned into numbers, and certain numbers mean particular words, and they're related to other words like conflict or war. They're similar words. So now we have a database full of numbers. Okay, so that's not very interesting, is it? But we also store the content. So the content is the text that got pulled in. The vectors is where the interesting thing is going to happen. So now we come to a system where we're going to interact with it. So let's use the chatbot example, but like I say, agents and other styles of interaction can happen. I come and ask a question. I say, what did Biden say about the war in Ukraine? That question uses the same model, the same encoding model, to convert the question to a string of numbers. So now the question set is a set of numbers. That goes into what's called a similarity search. And the similarity search is basically when the maths happens, and we do some what's called finding the distance between different numbers, which is really cosine. And if you're interested in the maths, we can talk about that. But essentially, it works out that those chunks of text are probably relevant to the war in Ukraine, and those bunches of text are probably to do with ice cream, and they're not very interesting. Okay, and once it's got that back, and you get the however many chunks back that you think are relevant, so you might hear this phrase top K, you're bringing back the best fit, the best matches. And then the vector store database goes and gets the actual text that was associated with those chunks from that retrieval. So now you have some interesting text. You put that text together with the question, what did Biden say about the war in Ukraine? That context and question are fed to the LLM, the foundation model. LLM does its business, generate text, inference, and it comes back with a much more meaningful answer, and it actually returns information about things that were said in that 2022 speech, because that's what went into the vector database, as opposed to some general things Biden may have said or other people said about the Ukraine war that's embedded in the large language model. Okay, so far, right. So what happens with Graph? So Graph basically improves this a lot more. So we'll explain a little bit of Knowledge Graph. Thanks, George, explained it well, but if you think about those chunks and documents, those are pieces of information. And obviously we want to relate those pieces of information together, and we do that through what graph calls edges, so the lines between the boxes. And in this example here, a couple of examples here, something about the Space Needle in Seattle. There's some text about the Space Needle building, and we know there's some information about Seattle, the city it's in, and I think Lower Queen Anne Street is the street it's on. But the point is, okay, so what is the Space Needle? Oh, well, it's an observation tower. What is Lower Queen Anne? It's a street, it's a location. So now we're starting to build concepts and interesting meta information about the overall document set, the input text. So this is the knowledge graph. So what happens in a graph RAG system is we're trying to find much more additional relevant content to help us with our interaction with our Q&A. Okay, so it goes through a number of steps in that process. In this ingestion process, like we were doing before, at the time of ingestion, we can also analyze the input information and generate additional metadata that essentially defines the graph. So we create metadata items which are the edges, essentially. And that gets embedded as numbers, and that goes into the vector store alongside the regular information. And then when we come to do our interaction, when we come to do our retrieval, instead of using a standard database retriever that's been built up over the years, we use what's called a graph retriever. So people have built these graph retrievers. We're going to show you the ones that work with the Astra database platform. And the graph retriever knows how to navigate that metadata, essentially the edges. And the result is number 3. Instead of coming back with 3 documents or chunks that what was interesting about in the context database, in the vector database about the war in Ukraine, it goes and finds some more relevant chunks because they're related, because the knowledge graph is directed that way. That means the piece of text that's assembled as the context to go into the large language model is bigger. And it's got more information relevant to the question, i.e. what was ingested into that vector store originally. So step 4, standard process with the LLM, but this time more context has gone in, so more information has been retrieved. So if you can build RAG-based systems using knowledge graph, and that knowledge graph is interesting things, perhaps it's like George's code-based analysis, then we're going to get much more accurate and meaningful responses as opposed to using either just the standard vanilla LLM, just chatting to it one shot, or RAG systems, which popped up a lot in the beginning. So, without further ado, we're going to give you a little demo, and then when Erol's ready, you can grab the cable. And after the demo, we've got some links. We're going to show you a few pictures in terms of, oh, that looked easy, what we're about to see. Now let's think about what the reality of making that in a big system is. Okay, thanks, Erol.
Well, where do we start? So, I think from a technology stack perspective, just to highlight what we're utilizing. So we've decided to use IBM's Astra DB database to store our content, as well as creating our vector embeddings, and we can access that information. Everything you'll see today will be a SaaS offering, so we have the ability to consume this via the cloud. We are also using our watsonx AI platform. Again, SaaS offering, like a catalog of information and access to large language models, just like you would do with ChatGPT or Gemini and so on and so forth. So we made a conscious decision to use a particular large language model, and I guess I've got 2 specific demos. I'll run through that as well, just to briefly explain, because I have a very bad memory. So the first example is a simple in-memory RAG pattern. So we're going to execute this. We're going to store out an array of vector embedding information as part of that. So we'll use our vanilla large language model again through the IBM stack, ask it a question, get a specific response. Then we'll move on to the more advanced RAG pattern, which will use the data that we have to provide context to the actual large language model so that it has the ability to enhance the actual response itself. So the vanilla LLM will basically use pre-trained data sets with no context from additional information, whereas we will provide it context and then we will access it via a vector database, and then that graph retrieval that Jeremy was explaining will give us context back to the actual prompt query, and then as part of the response itself, we'll provide a more refined context response as part of the prompt itself, right? So why does this matter? It's going to show us that the gap between our knowledge graph. Big organizations ask these questions all the time. I have a whole heap of information that I have stored across different silos. How do I access that information? How do I know my knowledge graph factors in everything that my organization needs as part of a particular response? What we will not demonstrate to you today is the ability to do AI explainability. How do I know that my actual large language model is executing correctly? Whether there's the ability to explain, whether there's trustworthiness, there's truthfulness behind this. The other part we will not also show you, which George sort of hit on the nail as well, around business context to your knowledge graph, is guardrails. How do I make sure that policies are in place to put a guardrail to stop it from hallucinating or even obfuscating data when we actually perform a query? And that is part of the broader spectrum of your knowledge, right? Some parts of the knowledge graph has to be obfuscated away from the business due to maybe security reasons or whatnot. We will not demonstrate that today. It's just going to be a simple request and a response. Obviously, Jeremy's explained how we've chunked up the data. He's explained the semantics around the search itself, the mechanism on retrieving that as well. And basically, I'm not going to run through the code. I'm going to make it very simple for us. So
we got the GitHub repo at the end of the link, end of the top.
But think of it as a subset of questions that we've placed into it, and we're going to execute this. It's going to go and do its magic. So I might just collapse, and I hope everyone can see that. My eyesight's bad. Collapse all the code base, and we're going to just execute the cell. Again, we're just looking at the difference between the response between a pre-trained data set using a large language model based versus the context of data that we've provided, right? And again, this is in memory. The advanced demo that we're going to show you next one is a bit more advanced than that. So again, we've connected up to our large language model. We've inputted some data. We've stored that data in memory using, if you really want to get technical, it's called NumPy. You can go look at that Python module yourself. And again, we've looped through, we've asked the questions, and basically we've got a vanilla large language model response with no context. So think of it as it's just provided a response based on this data set. And then we've actually gone and looked at the RAG enhanced response, which has taken time to go look at the data that we've provided, as well as this pre-trained data, and rationalize the context of that actual output back out. Okay. Move on to the next one.
Yeah, so I maybe should have made the point earlier. Of course, when you go talk to ChatGPT or Claude, whatever, and you ask it when was your last training date, and it'll say something like September 2023. Obviously, they're training these LLMs on gargantuan amounts of data on lots of CPUs, so they don't do it every 5 minutes. So they've only got knowledge, they've only got the internet up until a particular date in time. You'll probably see with Claude and others now, you can see them, I haven't got that information, I'm going to go search the internet, search the web. So they're starting to build RAG into their interaction, but when it's a RAG that Erol's showing you, this is now information that's relevant to you.
Yeah, it's a point in time localized to my execution of where I am here right now, right? So what Jeremy is explaining is the orchestration beyond the state of where I've executed my request to a set LLM. We do have an orchestration capability built into our platform as well. We're not going to show that to you. It's called Watson Orchestrate. Just maybe very briefly, because there's so many components.
Well, that's the thing that's running on Grok, isn't it?
Right. So yeah. There's so many layers to this, but the orchestration component can be built into your prompt mechanism. There's a scenario where you do have to go out to the web. You do have to query for certain points of information to add context back. You can do that. But large organizations like banks are avoiding scenarios like that because, one, you get hallucinations, the response may not be accurate, and obviously the data that you have within your organization, you do not want it to leak. Yeah. Right, so these are things to consider.
And just before we jump across then, so what, you can run this code later, but what's happening now is you'll see that it's a bit small, it says RAG generated content. So the information there that's in the answer to that question, you can go off to the text file which was ingested, and you can spot the text that was in there, so you know that it's pulling this relevant information, i.e. the text file, into the answer that it's composed for you.
Just thinking whether we need to talk about similarity searches. The answer is no. We talked about chunking. Does everyone understand between how we've chunked up a document, we've split it up, we've actually created a vector in their embedding, we've stored it up into a vector store. And
Lidos is off.
Yeah. and basically, the RAG response is looked at the top 3 chunk, right? You can tune that to your liking. Remember, performance, the deeper the question, the more you're trying to retrieve, the longer the response it takes to respond, the more computational power that you actually need to respond to do that. So that's why you see companies like OpenAI going quite heavy with trying to build large data centers. Sorry, you have questions?
Just generally, like you output like the text results, but how do you evaluate now the quality of it?
So that
get it to us?
There is a mechanism. It's not demonstrated here. Inside Watson-X, we have a component module called governance. And what that does is it uses OpenScale to pull in that volumetrics to be able to manage and monitor your large language model. And it'll use specific points of data to determine whether there's actually a level of hallucination, content that's being generated because of that hallucination. So we have the ability to monitor that. Again, when you go back to, guardrails, there is a guardrails mechanism inside Watson-X governance as well. As you're putting those policies in place, you'll see it either adhere to that or not adhere to that. That will also add to OpenScale as well. I wish I had time to write the code for that. It doesn't take long. It's only maybe a couple of hours, but I did not for this demo. So it is there. Watson-X governance is what you can look at. That will do exactly as you requested. Cool. Okay, so the more advanced RAG pattern, or what we call graph enhanced RAG pattern. So how do we get into this? So what we're saying is we're addressing the limitations around a standard RAG search using vector search. So again, looking at chunks, what they call semantically adjacent, but not mathematically similar query. I have to read that out because I completely forget. What we're doing now is we're going to be ingesting data, we're going to be chunking them up, we're going to be tagging them with metadata. So there's going to be element IDs that we're going to pull out. Those chunks we call, to your question from before, it's called node. And as part of that node creation, we create that metadata, which will create the edge relationships between those nodes. So as that knowledge graph grows, we can show a coincide relationship between key words, and those elements will help us determine how deep we want to add context to a query request that we make to a large language model, how deep we want to go into that. And the better thing is, the deeper we go and we understand the relationships between those different chunks, the better the response is going to get. One thing that we really should, most people should consider, it is very much an evolving space. Me and Jeremy cannot put our hand on our heart and say what we're demonstrating to you today is the solution to everything. It is evolving. We will demonstrate one element. There's a document that I've got at the end of this that I'll show you, a table which has three different types of methods that you should consider, plus more. And the question we always get asked is, Erol, can I use one particular one? And the answer is no, you can use all three if you want. How you ingest the data, how you process the data, how you tag the data, how you actually do a query search on the vector database itself to retrieve that embedding to be able to add context to your response. So these are all things you need to consider. And yes, it has a performance impact. Yes, it costs money because you've got tokenization consumption that goes up. So more computation. These are all considerations that you need to factor in. So again, I've got another Python script. In this case, we're not calling a localized vector database, NumPy. We're actually calling the Astra DB database. We've got a set of questions based on the union speech. what did Biden say about Ukraine, what did Biden say about inflation, and what did Biden mention about COVID. And I've shown you the standard RAG. We're going to see the standard RAG output response. Then we're going to see the augmented graph RAG response. And we're going to see the differences in the actual context and the response that you're getting out of that. So I'll just collapse Codebase.
Whilst Erol's doing that, I mean, I think the inflation question is a trick question, really, because I checked this with Claude. If you ask Claude, what did Biden say about inflation, he goes, I don't have any context. There's so much information on Biden. It then goes away and has a guess and goes and gets different sources, but it doesn't really know. It means we know, because we're the humans, that the question is being asked in the context of the 2022 State of the Union speech. So that's the point of showing the vanilla LLM comes back and goes, but the graph RAG comes back with much better information.
Just one little thing to sort of highlight, I was mentioning 3 or 4 different types of methodologies to write this. We made a decision to use keyword. So yes, we're using a graph, we're using a text splitter to split the chunks up and tag the nodes. We're then using keyword to be able to search for specific keywords. We're then creating the metadata information. That metadata information is then appended to the existing document chunk that we have. So you get this little ball of information that's been pulled together, and then we're uploading into the vector database itself. That is what is giving us a vector embedding query to be able to search for those specific numerical values when we do our graph retrieval. All right, so very important to highlight, yes, it can be done a different way. This is just the way that we have chosen to do this. You can go look it up, it's called keyword link extractor. So again, we use that, and that will be used in coincide with our graph retrieval process, or what we call a graph traversal search. And we have the ability to decide how deep we can go when we run that graph query, that traversal search query. Okay? You can go K-10 or whatever you want to decide to do. So, just a very brief example of the output. We have a question here. What I say, we have a standard vector search. So it's gone to the vector database. So I should maybe say that we loaded both the original documents without the metadata and the secondary parts into the collection. We also added the data.
So just back to that then, the top half is the standard RAG and the bottom half is the graph RAG, yeah?
Yeah. So just structured versus unstructured. Can we pull unstructured data and put it into a structured database like Astra DB? Absolutely. This is what your data will look like. Might just do it via JSON. We've pulled in unstructured data, or if you want to pull a PDF file, great chunks, and we can restructure it. And the output of the standard doc versus the enhanced metadata this is exactly what our graph retrieval process will go through. This is what the data looks like in your actual vector database, right? So when we do a query, again, we're looking at specific numerical values, keyword matchings, and then we're also then looking at how the large language model will use the interlacing matches between the relationships of the nodes and the keywords to pull even more data down and be able to provide a better context in the response. And these are just some of the key. So the metadata is the section that we've appended to the original document. And then I'll just go back to the question. So standard versus graph RAG response. Retrieve chunks, you only get an X amount of chunks, 1, 0, and 8. We have far more retrieved chunks in the below graph RAG response. Why? Because it's used those edge relationships between the nodes to determine that there is key links between the actual phrasing information in the content.
Yeah. So again, if you look at these two pieces of text, they're both RAG. They both use that same input speech as their data, but if you pick through the words of the response, you'll find them, you'll get to the first one and you'll find them in the speech, no problem. But then you look at the second response, you find, oh yeah, there are some other parts of the document which the standard RAG didn't pick up, but the graph RAG did. So you're getting a richer response.
I'm going to quickly show you what a relationship mapping looks like between chunks. This is essentially it. So we've visualized an output response from the vector database using the respective vector embeddings. This is outlining the chunks that have a relationship by the keywords based on the graph retrieval process that we've executed. Okay, so you could hover over it, for example. This is basically a key, this particular sets of keywords, so COVID, vaccinated, vaccine, etc. The blue illustrates, let's call it a primary key or principal value, and then we'll have smaller key chunks that have further relationships between the primary key values.
Cool. Good.
Good.
All right, thank you. So let's flip over to this. I'll give you the link to the repo, and obviously can take questions after the event. Nope. Oh, there we go. All right. So you'll look at the code and you'll understand it. You may have even done similar yourself. But to be all honest, it's trivial. It's experiment. It's an experiment. I talked about fine-tuning, RAG, size of model, that type of thing. What you generally have to do is start thinking about the architecture around essentially the code that you're engineering. And you'll find, because I think what we're finding now is in the past years, shall we say, architecture have led how to design systems. But then there's a growing last few years of engineers actually understanding how the implementation of the code works. So everything that Erol was explaining, sort of the complexities of the splitter, the embedding model, the graph retriever, which one to use. These are all software decisions to make that script work, but now they're becoming much more relevant to the deployment architecture. So just down the left is like 10 things to think about. There are 100 things to think about when you're deploying one of these systems to production. But let me just throw a few at you. So if you think about, okay, I've got an application, let's call it my chatbot. I've given it's already got the data ingested. We'll come to that in a minute. I ask a question, what about the war in Ukraine? It goes off to the AI system, has this RAG interaction, which touches a large language model, which is huge and sits on a small island of GPUs to do the work for you. Where do you put these different software components and databases? So if you think, I'll tell you now, a vector database, unless it's properly secured and it's a decent system like Astra, a vector database is reverse engineerable, which means you can go and get those numbers, you can apply some clever tricks, and you can find out the content in that database. So the sensitivity of the information in a vector database is just as important as the original source system databases that the data came from. So now you've got an application essentially interacting with a vector database, which is then going to send some information to a large language model hosted somewhere. Most of the large language models these days you get access through the clouds. You've got Amazons, you've got Azure, etc., Google. And then those models are loaded up and running on the GPUs in their data centers, operate as SaaS service, excellent. But you're going to push some data in, your context, employee records about me. You're going to ask it a question, and it's going to come back with an answer. Therefore, you need to know that pipe of data back and forth is secure. Where do you put your vector database? Do you put it next door to the endpoint inside the cloud? That can be done, of course. You just got to make sure that you secure it appropriately. Or do you put the vector database on premise, maybe where your application runs and where the source systems are? That's a good idea as well. But then remember that the egress data fees from the cloud to the on-premise for every response has a factor. So these are some of the non-functional requirements we go through and think about when we're building architectures. And also, I mentioned at the beginning, the size of the models. You don't always go off to ChatGPT to ask it what the weather is in Paris. That'd be crazy. But people are doing that in these big banks and governments that we have, and spending a lot of unnecessary money on tokens and GPUs. So I think the main message is the engineer has the insight how the code is interacting and how the data is flowing. And it's getting more and more complex, so you have the power to influence the architecture. What we've used today is just a small fragment of the power of essentially two platforms we have, What's the Next Data and What's the Next AI. So today we used some basic code storing in the Astra DB vector database, but there's things like Unstructured.io that we partner with. They're an excellent tool for splitting all sorts of documents into all sorts of shapes, and there's different options in terms of data lakehouses, Milvus vector databases, Parquet formats, Iceberg, all the jazz words around data platforms this world. And then Watsonx AI itself is built on a platform from Red Hat called OpenShift AI, and that's essentially a platform that can host a myriad of different models, from machine learning through to foundation models. But again, back to the architectural thinking, it has things built into it like VLLM, gateways that control the traffic in and out of a model. The platform is trusted and enterprise secure, so it only goes and talks to LLMs that have been approved by Red Hat and various indemnification clauses. And then there's all the build tools underneath, the pipelines for building. So if your employer of choice says, can you build me a data and AI platform, go fill your boots. All the open source software is out there and you can do it. All I can tell you is it's a bit complicated once you get going. So hopefully you'll go and buy one, hopefully from IBM or maybe from somebody else. But we've got, it's been a pleasure talking to you today. There's our LinkedIn links under the fancy bit.ly codes, QR codes. There's a graph repo there, and I'll post on LinkedIn tomorrow. We've got the slides on SlideShare, but if you just ping me or Erol on messengers in LinkedIn, and we'll send you the slides if you want. Okay, thank you.